Okay, so welcome back. We're going to go into something that seems like a little bit of a departure from the usual discussion of calculus, and that is we're going to talk about limits. And like I said, this might seem like it's kind of out of the blue, but the reason we talk about limits is because derivatives and also indefinite integrals, and actually definite integrals as well, are defined in terms of a limit equation. So you have to understand limits in order to really understand all three of the major calculus operations. So with that, let's dive into it. What exactly is a limit? The limit of a function f at a point A is the value that f approaches as it gets infinitely close to A. Now, this is a very technical definition, but there is absolutely one key word that you need to understand, and that is approaches. It is not the value that f takes on when it hits A. It's the value that f approaches, that f gets close to, as x gets close to A. In other words, as you move along the graph towards the point A and f of A, what number do you get near if the trends continue, not what value do you actually take on. Okay, a little bit of notation. This term here, this term here is read as the limit as x approaches A of f of x, or the limit of f of x as x approaches A. So what is the difference between the limit of f of x as x approaches A and f of A itself? In other words, what's the difference between taking a limit as you approach something and just plugging the number into the formula? Well, sometimes they're the exact same thing. Now, like I said up here, a limit is the value that f approaches. And so really what limits do is they follow the trend set by the rest of the function, not necessarily the value of the actual point of interest, the value of f of A. It's more determined by the points around f of A rather than the point f of A itself. Okay? So I said sometimes the limit of f of x as x approaches A is the same thing as f of A. There's a sort of general rule as to when this does and does not happen. If the trend of your function suddenly changes at point A, then the limit and the actual value, in other words, this thing and this thing, are going to be different. But if the trend stays the same, then the limit and the actual value are the same. Okay, let's take a look at this. Helps to have a concrete example. So let's start with one that is seemingly so simple that it's trivial. Let's look at f of x is equal to x plus 4. This is a straight line. And let's... Okay, so straight line, y-intercept at x equals 4, slope of 1. And let's say we're interested in this one particular point right here at an x value of 2, and that gives us, based on substitution over here, that gives us a y value of 6. In other words, f of 2 is 6. Now, let's take the limit of f of x as x approaches 2 and see if we get the same thing. Okay, so if we approach 2, there's two directions we can approach from. We can approach from the negative side heading towards the positive side, and that's represented by this red arrow here. Or we can approach from the positive side heading towards the negative side, and that's this arrow here. And both of those trends converge on the same point. And that point where those trends converge also happens to be the value of f of x at that point. And so, not surprisingly, we can just substitute the value of 2, the limit, into the function, calculate everything, and get a real answer of the limit equaling 6. So in this case, the limit is 6 and the function is 6. In other words, the limit and the value of the function are the same thing. And this is true because, as I said earlier, the trend stays the same. In other words, the point f of 2 continues the trend set by the points around f of 2. Alright, now we're going to do a tiny variation on this problem. Alright, we still got the x plus 4 part here. The x plus 4 is here, x plus 4 is over here. All I did was multiplied by x minus 2 over x minus 2, which creates this new function g of x. And this, by and large, changes absolutely nothing, except at one point, and that point is x equals 2. If you try to take g of 2, when you substitute the 2 into here and the 2 into here, this gives you a 0, that gives you a 0, you end up with 0 over 0, and 0 over 0 does not exist. So the function does not exist at the point 2, at the point x equals 2, and that's why we have this open circle here. The open circle represents an infinitely small discontinuity, a gap in the graph, but it's just one single point, that one single point where x equals 2. If x equals any number other than 2, 2.0000000000001, we will get an answer that does exist. Or similarly, if x equals 1.999999999999997, then we will get an answer that exists as well. It's just at that one infinitely small point where x equals 2 that we get this weird does not exist answer. Alright, so the value of the function does not exist, but let's look at the limit. If we take the limit as x equals 2 of g of x, then remember, we're not looking at g of x at the point where x equals 2. We're looking at g of x around where the point, around where x equals 2. So we're going to approach it, again, from both sides and see where those two trends converge. And as you can see, just from the direction of these arrows, these points converge on this point. In other words, the limit of g of x as x equals 2 is just following the linear trend, and during that linear trend, in other words, at points where x is close to but not equal to 2, this part and this part will cancel out, and that means we're just left with x plus 4. We substitute the 2 into there, and we get 6. Okay? So in this case, the function does not exist at x equals 2, but the limit does exist at x equals 2. The trend set by the points around g of 2 determines the limit. The function determines the value of the function. The actual equation up here determines the value of the function. So that's the key difference between a limit and the actual value of the function. Now let me just make a couple side notes. You will get a few really simple limit problems like this. These will probably take you about 5 seconds to do. It'll take you longer to write it out than it does to think about it. But an important time when limits give you really useful information is when you run into these points where you get 0 over 0. You have to have a 0 in both the numerator and the denominator. And the reason for that is that if you just have a 0 in the numerator, then your value is just 0, because 0 divided by anything other than 0 is 0. Now 0 divided by 0 is something kind of weird that varies from one equation to the next, and that's why you got to take limits. Okay, so always try the simple solution first. This is sort of a problem-solving guide for the relatively simple limit problems that I'm going to expect you to solve for this class. If you take a real full-blown calculus class, you will learn some much more sophisticated ways of solving for limits. I consider that to be outside the scope of my my class as a physics preparation class. Okay, so always try the easiest solution first. Always try substitution first. It's like the first rule of lockpicking is to make sure the door is locked. Okay, or check to make sure the door really is locked. If you can get by with substitution, and you'll know you get by with substitution because your value, your function will spit out a real number, then congratulations, you're done. That's the limit. That's like the situation on the last slide where we worked out f of x. If you get 0 over 0, then try simplifying the function before substitution. And there's 4 main ways you can simplify. You can factor and cancel, which is essentially what I did with the g of x function. I took the factor x minus 2 and canceled it out in the factor x minus 2 in the numerator, canceled it out with the x minus 2 in the denominator, and was able to then substitute and solve. You can also do something called rationalizing the denominators. If you have by the way, factoring is particularly useful when you have polynomials. All right, if you have a polynomial in the numerator or the denominator of a fraction, try factoring it. Chances are something will cancel out. All right, getting on to rationalizing denominators. When do you rationalize denominators? You do that when you have a square root function in either your numerator or rationalize the denominator. You use it when you have a square root function in your denominator. And this might sound like gobbledygook to you, but if the way you rationalize a denominator is you multiply by both the numerator and the denominator by the complex conjugate of the denominator. If that made no sense to you at all, don't worry. In the upcoming videos, there's going to be an example of that. If you have to do any addition and subtraction of fractions, do not forget what you learned in grade school. Find the lowest common denominator or the least common denominator. In the process of finding the least common denominator and adding and doing your addition or subtraction, again, you might end up with a polynomial that you can then factor and cancel. Last but not least, if you have a compound fraction, that is something like a over b over c over d, you can simplify that by multiplying by the reciprocal of the denominator. Again, if that made no sense to you, don't worry. There's going to be examples of it in the upcoming videos. Okay, so I laid a lot of responsibility on the upcoming videos, and the reason I did that is because I didn't make them. These were excellent videos made by on the YouTube channel pastcalculus.com, and it covers it has a series of 3 videos on limits. After the 3rd video plays, you will once again be subjected to my videos. Now, I gave you URLs here. You probably will not need these URLs unless there's some sort of technical malfunction with the playlist. So these videos will start automatically if you're running the AP Physics C Prep Day 1 playlist. See you in the 4th video of